Hello everyone. Good morning. Welcome to today's webinar, Innovations in VisualSim for Architecture Exploration. In this webinar, I will be going over the new advances and the new technologies that we have introduced for ease of use and for increasing productivity of the model construction and analysis itself. As we have a lot of new people who has not heard about Mirabilis Design or who has not heard about VisualSim Architect, I'm going to go over the basics of technology and uh, going over a few items about what exactly the kind of analysis that we conduct and how exactly a simulation model can be constructed using VisualSim's predefined library blocks. Okay, so before getting into the presentation, I would like to go over a few items so you know exactly how to participate in today's event. And so here we have a sample attendee snapshot, attendee interface snapshot. You should be actually seeing this in the right-hand side of your desktop. There is a chat window and you can actually post in your questions, and we have people in standby. They will be answering your questions, and also I'll be taking up these questions later in this presentation itself. So for those of you just joining us, welcome to today's webinar, Innovations in VisualSim Architect for Next Generation Architecture Explorations. So to start off with, Mirabilis Design and who we are and what are the technologies that we are talking about. Mirabilis Design is a systems engineering company, and we are based in Sunnyvale, California. And our major motivation or our major products are actually around architecture exploration, power and performance analysis of your embedded systems, semiconductors, and complex electronic system architectures itself. So the models constructed using VisualSim Architect is actually used to conduct timing, power, and functional analysis. So the whole idea or the goal of conducting these simulations is to make sure that the selected architecture is going to meet your requirements in terms of performance, power, or reliability metrics. So in order to construct simulation models quickly and accurately, we provide customizable and configurable library blocks. And I'm going to show you the list of libraries that we are offering. And also we provide a large set of application templates or demo examples that enables a user to get started with modeling very quickly, and they can pick up any of those demo examples that is close to the user application and build their systems around it. Okay, so the product name is called VisualSim Architect, which is a completely graphical and hierarchical modeling and simulation platform. So when we say systems engineering or conducting architecture explorations early in the design phase, the major motivation for conducting architectural exploration is actually because of the kind of complexities that the modern systems architectures are possessing. One of the crucial characteristics that we see in almost all complex system architectures is limitations of resources. So it could be limitations in terms of processing speed or communication bandwidth, or it could be limitations in terms of memory access time, or if it is a battery operated system, then power consumption is going to be a crucial factor as well. And these characteristics, these kind of challenges directly has impact on the total system performance as well. And also these causes a lot of interdependencies between the tasks that you are running on the platform as well. So in order to understand what are the challenges that you are having or that you may come across later in the design process, you will have to construct a very detailed simulation model of your complete system architecture, including your processing board and your communication channels and interfaces and sensors and all the subsystems around it. And when you construct these simulation models and if you try to evaluate that particular system, you will actually you will have to look at the latency that you're getting for a particular application when you're running on that particular platform. And if you split it up and if you try to understand what is the communication latency versus what is the processing latency involved in that particular total end-to-end latency as well. So that actually gives you an idea about where exactly the problem is. If the communication latency is too high, this actually tells you clearly that the bandwidth which is available on the communication channel is not sufficient enough, and it started buffering up, and you're not getting the performance what you're expecting. If the latency in terms of processing is too high, then this actually tells you clearly that the processing resources what you have selected is not sufficient. Otherwise, the memory subsystems what you have constructed around the processing platform is not fast enough. So these kind of information will actually tell you, and also these are the challenges that you must address early in the design phase as well. And in addition to that, you need to make sure that all the real-time and hard real-time applications are executing in the given timing deadline as well. And it is not taking more time, or if it is not exceeding the timing deadline what you have given. So if there is any kind of lot of interdependencies and if the resources are not sufficient or not available, then you may actually end up exceeding the timing deadline, and you need to make sure if there are any kind of tasks that are exceeding the deadlines, you need to make sure you need to address those problems early in the design phase itself, and try to optimize the system architecture to overcome these challenges as well. So in addition to power consumption, because when we talk about a particular system architecture, we can't look into it only in one angle or two angles. We actually need to look into a particular system architecture success in three different ways. One is that you need to make sure the selected system architecture is giving you better performance, and you need to make sure the deadlines are not exceeded. And also at the same time, you need to make sure that the power consumption, what you're achieving for a given set of performance figures, is not more than what you're expecting. So power consumption is under the threshold. And the third part of it is making sure that the reliability of the system architecture is contained. And when we talk about power consumption, most of the scenarios includes, or most of the formal methods includes looking at the power consumption purely in terms of Excel spreadsheet computations or things like that. So Excel spreadsheet computations is actually well and good, but they provide only the kind of average power consumption of the system architecture, and they loses the characteristics such as a dynamic behavior of your system architecture itself. So if there is any kind of spike in the power consumption, maybe after some time, maybe if the total simulation runtime is about 100 milliseconds, if there is a spike nearly about 80% or 70% of your simulation time, that may actually cause the problems in terms of performance itself. So the performance of your system may degrade, or maybe later in the design process, that could become a major bottleneck in the system success as well. So you need to identify the instantaneous power consumption of your system as well. At the same time, what is the average power consumption of your system architecture as well. So with regards to if the system that you're working with is a battery operated power, so you need to make sure the selected battery is going to long for so much time period, maybe 5 years or 10 years or something like that. So you need to keep on monitoring your charging and discharging cycles, and you need to make sure that uh, based on the type of battery that you have selected, what is the rate at which you are charging and discharging, and also that actually tells you how long you can actually run this or utilize that particular battery itself. And you can actually try to understand, is there any way to improve the performance of your battery as well. And actually these are the kind of problems and the kind of solutions that you have to identify as early as possible in the design process. The idea here is that there are nearly about 60% of the problems, the kind of faults that you can inject at the architectural level, and the impact of those injecting faults and the delay caused because of that particular explorations is actually very less, as opposed to finding the challenges or the faults later in the design process itself. So looking at these particular challenges and the kind of problems that typically architectural space is coming into picture, we have actually composed our tool set to address exactly these kind of problems. So the major problems would be, how do I select my system component? So if I select a particular component itself, for example, a particular CPU or a microcontroller, why I am selecting it and what is the benefit that I'm going to get out of it? And also if I am running my application on my multi-core or multi-processor platform, how I need to split my software threads between multiple processor cores or multiple processor boards itself. So in order to get a better performance or things like that. If you have a system in which you have custom accelerators and you may have your application processors, things like that, and you want to understand how to partition your system into hardware and software part of your system components as well. So partitioning of your hardware and software actually predominantly depends on the performance that you're going to get by doing hardware and software partitioning, and also at the same time, what is the power consumption impact on that particular distribution as well. So by looking at these characteristics, we have actually provided a tool set which actually enables the user to quickly and accurately model a system architecture using graphical and hierarchical modeling approach. So when we say graphical and hierarchical modeling approach, we actually provide a large set of library blocks, both in stochastic and cycle accurate level of details. And these libraries are completely customizable and configurable, and user will actually drag and drop into the environment and configure them based on the particular vendor specific configurations or things like that. For example, if you're having an architecture with an ARMA AHB or an AXI bus with a particular processor core, with a certain set of memory subsystems, things like that, we actually provide you all these library blocks, including your hardware and software components, and that actually enables you to quickly assemble your simulation models. And one thing you notice over here is there is almost very little amount of scripting is required. And if you have any kind of models that are constructed using C, C++, or System C, and if you have constructed or defined any algorithms in MATLAB or Simulink, then you can actually directly bring in those models into VisualSim environment itself. So the major idea over here is to be able to enable a particular user to quickly assemble a simulation model, including hardware, software, and algorithms and interconnects, things like that, and try to conduct simulations, varieties of simulations by running lots of test cases and use cases to be able to capture the possible bottlenecks that may actually show up later in the design process itself. Okay. So here's a kind of quick view of a list of libraries that we provide. And again, this is not a complete a list. And here we have kind of frequently used library blocks from our customers. And we actually keep on adding library blocks based on customer requirements, as well as based on how a particular library is actually being utilized in various sectors. We actually add almost one or two libraries in a month, and we keep on adding these libraries uh, to be able to kind of enable a particular user to construct those simulation models as quickly as possible. Okay. To just kind of remind you, we have people in standby. If you have any questions, please post in your questions in the chat window, and our people can actually answer your questions. And also I'll be looking at those questions in between as well. So looking at the hardware architecture exploration, when we talk about hardware architecture exploration, it really means, well, what are the components that you're selecting and why you are selecting, and how you're defining your hardware topology itself, and how you are actually utilizing your hardware architectural resources to run a particular set of applications to achieve a better performance, things like that. So when we talk about hardware architecture exploration, we actually enable a particular user to size a processor, at what clock speed he has to run the processor, and how many pipeline stages that he has to have, and how many level of cache or memories that he has to use there. And also, in addition to that, the distribution of tasks between multiple cores of a particular processor as well. And with regards to memory hierarchy and cache memories itself, the libraries are extremely detailed and very accurate library blocks. And these actually enable you to be able to read and write the data to a particular memory location, and try to understand what is the performance that you're getting if you're using a particular memory technology from Micron or Samsung or things like that, along with your processor subsystem as well. So one of the major idea, or one of the major challenge that we are addressing over here is most of the kind of ISS or similar tools actually trying to understand or trying to evaluate the processor itself, and trying to understand what is the application, how that particular application is actually going to run on that particular processor core. So what we really do over here is, the major bottleneck that we have seen in a particular processor is not just with the processor, it is actually with the memory which is actually connected to it. So we actually try to understand or trying to explore the memory reference time related challenges, and trying to optimize those critical bottlenecks in the system design flow as well. Okay, and to be able to do that, we actually provide both standard and custom processor generator toolkits, and I'm going to show you that in a little bit as well. And the other part of the hardware architecture exploration is, if you have a scenario in which you have processors and you have application-specific integrated circuits, and you may have FPGAs as well, and if you have a very complex signal processing application or things like that, and if you want to understand how you want to distribute tasks between your processors and FPGAs, VisualSim actually enables you to map your applications between these different processing resources, and trying to explore what is the performance that you're getting with a different set of mapping methodologies. Okay, so at this point I would like to quickly go to VisualSim Architect tool right now to show you quickly how hardware architecture exploration can be conducted, and how one can perform hardware and software partitioning of a system as well. So I'm going to go into VisualSim Architect tool right now. I believe you can see the simulation model right now. And this is VisualSim Architect tool itself. And this is the place where you actually construct your simulation model, which includes both hardware and software part of your system. And also it includes a lot of analytical tools, and also it includes report generation tools as well. And in addition to this, we actually have added a power analysis tool as well, which actually keeps on monitoring activities that are happening across your system platform. And it actually provides me the instantaneous power consumption as well as average power consumption of my complete system, as well as individual component power consumption. So in this case, we have actually split the model into two parts. So the top one is actually my hardware architecture, and the bottom portion is actually my software behavior flow itself. So when I say the hardware architecture, these are actually the library blocks that we can actually drag and drop from the library panel in the left-hand side. And once I drag and drop a particular library block from the library list, I can actually configure this by double-clicking on this based on how much clock rate I'm running and what is the threshold limits that I've provided and what is the type of uh, arbitration that I'm using, whether I'm using a fixed point or round robin or a custom algorithm that I'm using for arbitrating between the ports of my Axie bus itself. And similarly, other models such as memories and processors are also modeled. If I go inside my ARM subsystem over here, we actually have the processor generator toolkit itself. So when I double click on this particular processor, this is actually configured for ARM Cortex-A9. And here I have a list of parameters that actually enables me to configure this particular block for a particular processor core. In this case, this is actually taking the ARM instructions, and I have a number of registers, and I have parameterized the number of or processor speed itself. And in this case, I have one level of cache inside my processor itself. So I can have 2 levels or 3 levels of cache over here as well, or I can have external to a particular processor as well. In this case, I have an external cache which is actually connected to an AHV bus. So with that little bit of information about how the architecture looks like, and in this case what we have over here, this is a multimedia system, and in this case what we have is, what we are looking for is about 13,000 macro blocks or matrices being processed within 20 milliseconds of time frame. Okay, and the power consumption of the complete system should be under 1 watt of power. So what we are doing initially is we are actually initially running all these different tasks what I have at the bottom on the ARM subsystem itself, considering I'm actually considering it as a software part of my system right now. So when I hit the run button over here, it actually provides me a list of plots, and a user can actually configure or customize these plots based on their requirements as well. So looking at the reports here, I'm looking at the average power consumption of my complete system, and I was actually expecting about power consumption should be under 1 watt. I am meeting my power consumption here. X-axis defines my simulation time. Y-axis defines my power consumption over here. And if I look at my performance plot, here I have, we were actually expecting about 13,000 macro block processing, but in this case I can see that only 6,600 macro blocks being processed at a peak. And when we actually looked at the reports that we have provided over here based on the throughputs and utilization of various resources, we actually have seen that rotate frame is actually the task which is taking more CPU cycles. So when you know a particular task is consuming a lot of your CPU cycles, what you can do is you can switch that particular task to a dedicated processor core. So what I'm going to do now is I'm going to move this rotate frame task over to a hardware accelerator, which I have connected to my ARMBA AXI bus. So that switching over is actually, we have configured the model for that, and this is just a parameter to match between one block to another. So when I say mapping, so what we have over here is I'm going to go inside this particular block, and we have a concept of mappers and schedulers. And this particular mapper block, what it does is it actually allows me to map the incoming instructions or send the incoming instructions to a particular resource. In this case, we are actually sending it over to an ARM processor core, which I have actually in the architecture at the top. And this is virtually mapped, and we call it as name mapping between your application flow to the architecture flow. Okay, so I mapped my rotate frame from ARM processor to a hardware accelerator, and again I would like to see if that is going to meet my performance and power consumption requirements. So when I again see my power consumption report over here, initially it went very well, but later on the power consumption of my system started going up gradually. So this actually tells me that there is something wrong in my system architecture and some component is consuming more power than it should have been. And if I look at my power performance or number of macro block processing, it is actually now 14,600 macro blocks are being processed. So I was actually expecting about 13,000, but we are getting more than 14,500 macro blocks are being processed. So even though you're meeting your performance requirements, power consumption is again a bottleneck here. But when we looked at the activity of different components, specifically activity of the hardware engine itself, so it actually shows me hardware engine is always in on state, whether you have something running on the platform or whether you have nothing running on the platform, it is always on in the on state. And when I look at the individual power consumption, I can see that nearly 35% of my total system power consumption is consumed by hardware engine itself. So this actually tells you this is completely wrong. So what you can do is you can actually inject or introduce a power gating algorithm to make sure that whenever something is not running on your hardware accelerator, you can turn it off and bring it back when you have received a particular interrupt or things like that. So again, I'm going to run my simulation here, and looking at the activity of my hardware engine, you can actually see that it actually goes up for a very shorter time period and it is pushed back to zero state after that. And looking at the power consumption of complete system, it is under 1 watt and it is meeting my requirements. And looking at the performance, we're actually expecting 13,000, but we are actually getting 13,300 macro blocks are being processed. There is a slightly degradation of my performance when we have introduced the power gating algorithm, but we are still meeting our performance requirements quite well. So this is how actually you can construct your simulation model and use it to kind of explore varieties of scenarios to make sure the architecture what you have selected is going to meet your current as well as future requirements in terms of applications what you're running or the kind of algorithms that you're going to update or things like that. So at this point I'm going to go back to the presentation now. So looking at the types of results that helps you to make decisions on selecting a particular component or a particular algorithm, things like that, we actually look at the end-to-end latency or processing delay that has been happened, and we look at the throughput, whether it is in megabytes per second or megabits per second, or how many number of instructions that you have processed in your processor itself, and also looking at the utilization of various resources as well. And all these values will be provided in minimum, maximum, and mean. So that actually provides you a kind of greater picture about the kind of changes that are happening in the reports that are being generated as well. Looking at the process itself, we provide a lot of information on the internal caches and execution units and registers, and what is the activity that are happening in the pipeline itself, and how long the processor is in stall state or things like that as well. And also user can add additional or customized report generation capability to be able to narrow down the exploration of the hardware architecture platform as well. So looking at the software architecture exploration, we actually provide in multiple ways. We actually enable the designer to model the software behavior as a sequence of tasks that are being running. Or we actually enable designer to be able to generate a profiler-based instructions for the applications that they are planning to write. Or we can actually take the real applications what they have, and if we can generate an instruction trace for the applications what they have, and we can actually bring in those instruction traces as a input file for the target platform, and trying to explore the performance that has been achieved for the applications that that we are running on the target platform itself. So at this point, I would like to go over to VisualSim once again. I would like to go to a model right now, and this is actually the AutoSAR model. And in this case, what we have is we have an ECU and we have the runnables on top, which are actually going to run on top of the ECUs over here. And in this particular case, what we have done is we have defined the schedule tables and the task tables and the priorities, everything as a spreadsheet or in terms of tables itself. And this can be replaced by an application software code as well. And if you look at the schedule table over here, this actually tells me at what point a particular task is going to be invoked. And also, if I look at the task table over here, this actually tells me what is the runnable that you're going to run on the ECU, and what is going to be the estimated execution time of that particular task on the target platform itself. And also this provides you the priorities assigned for different tasks that you will be running on the platform itself. So when I run the model at this point, in this case, I'm actually looking at the timing diagram for the applications that I'm running on the platform. If I zoom into a particular region over here, if I zoom in a little bit more, so these timing diagrams actually tells me the dependencies between different tasks that we have on the platform. And also this tells you the impact of these dependencies on the total system performance as well. If you look closer over here, we have the T1 related tasks that are at the bottom, and also we have T4 related tasks at the top over here. And as T4 tasks at the top are actually having higher priority, that actually completed processing only after 0.104 milliseconds. And only once we have finished the higher priority tasks, the next higher priority tasks has been taken up. And this is actually showing me how long I am actually running a particular task and when it is going to finish. And these tables or these kind of timing diagrams allows me to kind of exactly understand what is really going on in my platform, and what is the impact of those task executions on the total system performance as well. Okay. I'm going to switch over. I'm going to switch over to the tool again. So with that little bit of introduction to VisualSim Architect and what we have done, or how an architectural level exploration tool can be utilized to perform performance analysis and power analysis at the same time, I'm going to now move over to the kind of enhancements that we have done with version 1620. And the enhancements we actually considered in 4 different stages, I would say. And these different parts would be are focused around ease of use and infrastructure and programming and interfaces capabilities, and finally modeling enhancements as well. So when we talk about ease of use, it is actually mostly around how easily you can construct those simulation models and how you can reuse those simulation models for later in the design process, maybe as an input for the implementation teams as well. So here we have what we are providing in 1620 releases. We are now generating a complete documentation for the simulation model that you have constructed, and we are exporting these model as well as documentations into a HTML page. And if you put this particular generated document on an Apache server, you can share these simulation model as well as HTML page, which is having the documentation, with the people who are actually sitting in a different country or in a different geographical location itself. So without having the software installed, user can just look at the HTML page, and VisualSim tool along with the model will actually come up right from the web browser. So they can construct, or they can conduct varieties of simulations by changing the parameters and changing the test cases, or changing the topology, things like that as well. So earlier we actually had just a kind of HTML view, and there was no provision for pop-up option of the model itself. And now we provide a lot of features such as exporting of images and other model related details. And also now we provide importing a library directly into the user library itself. So if you have any kind of project specific libraries that you have constructed, which is local to your office or organization, you can actually generate one, and you can import it to the library section as well. I'm going to show you that in a little bit. And in addition to that, we have improved a lot in terms of graphical user interface as well. And now we provide drag and drop methodology for hierarchical block as well. Okay. And in addition to the ease of use, we provide a search capability for libraries and models. And also the organization of the library folders are completely changed right now, which are actually close to or similar to UML and AADL methodology. At this point, I'm going to go over to VisualSim right now to show you how or what are the changes that we have done. And if you look at the new block diagram editor over here, in the left-hand side, we have the set of library blocks all the way from a document to interfaces and buses. These are the kind of libraries that are being used by hardware architects or avionics engineers or networking engineers or semiconductors or things like that. So these are libraries are easily accessible and are frequently used itself. And there is a kind of full set of libraries under a full library section over here. And I can search for a particular library from the find button over here. I can say, for example, if I type in a processor, it actually go to the processor model itself, and it actually brings me, I can quickly access those processor models as well. Okay, and if I look at the model, okay, again, and if I have to kind of look in or try to understand where I have used a particular parameter. Let us say I'm looking at processing speed or processor speed or something like that. I need to go to graph and do a find, and if I say processor speed, this processor speed parameter is actually used by this set of different library blocks, and when I double click on this particular one, it actually directly goes there and it highlights that particular parameter itself. So this actually enables you to kind of configure quickly and try to match it where exactly the set of parameters are being used. Okay, so in addition to that, we have added a lot of information to the Power Manager. So, or the Power Analysis tool. The Power Manager that you're seeing over here, it actually has a table with list of components that you have in your architecture, including your processors and caches and memories and other devices. This actually takes a certain set of power values. For example, what is going to be power consumption in standby state or active state or wait state, things like that. And these values can be collected from a particular device data sheet itself. And these can be entered in an Excel spreadsheet, and you can directly import it into the tool itself. And we have added a lot of additional features to it, not just looking at the power state. What we're doing is now we are providing the capability to be able to enter power expressions and trying to understand what is going to be the leakage current and what is going to be the idle current that you're getting with different states of your loads as well. For example, in this case, we have the models of PLL, clocks, and batteries, LDOs, and different loads connected to it. And the power manager is actually having different components connected to it with different states. And the tables that we have in the left-hand side, this actually tells me or enables me to compute the leakage current or the idle current based on our different states over here, different states for different components. And these expressions can be imported or added up to get more and more accurate power consumption values as well. Okay. And in addition to the modeling enhancements, what we've provided, now we have libraries, latest libraries of RapidIO. And specifically RapidIO, we have vendor-specific library now, and it is IDT RapidIO switch. And in addition to that, we have Firewire, Fiber Channel, Switched Ethernet, AFDX, and SpaceFire, and OpenVPX. These are the kind of libraries that we have received are generated or developed in this particular financial year or in this particular release itself. And with regards to memory technologies, now we are providing very detailed memory models for LPDDR2, 3, 4 or DDR3 and 4. And you can actually configure the memory block by using a Excel spreadsheet or a CSV file itself now. And to give you an idea how exactly this looks like, I'm going to go into the library here. And when I look at the memory controller here, this actually, this is a parameterized one. You can actually set this to either SDR, DDR, DDR2, or LPDDR memory technologies. And you can define the message timings or other memory timings for whether it is for TRCD or TRP and all that. And also you can provide how many banks that you have over here and how many columns that you have, what is going to be the burst length over there, and what is going to be the kind of custom arbitration if you are having in your customized memory controller technology, things like that as well. Okay, and these memory controllers are highly accurate, and they provide nearly 99% of power consumption values as opposed to the implementation level models itself. So these models are highly accurate now. And with regards to processor, now we support preemptions and interrupts and running multiple threads on the multiple processor cores. And also we have now provided ability to kind of call a coprocessor and hardware accelerator right from the processor pipeline itself. Okay, and also we have provided, or we are providing a processor generator kit as well. So that enables you to quickly assemble up a custom processor based on, I mean, that particular custom processor could be a processor from your organization itself. So this particular tool set with the processor model and an instruction set enables you to kind of enter all the mnemonics that you have and the latencies for that particular mnemonic. And then these particular these parameters enable you to quickly configure these, how many number of caches that you have and how many registers you have, and your integer execution units and floating point execution units and the pipeline stages itself. So when you configure these things together, this actually works as a um, cycle accurate processor model for conducting architecture exploration and performance analysis itself. Okay. And with regards to the simulator itself, right now we are actually providing a capability to run parallel simulations on your multi-core processor platform-based laptops or desktop itself. If you have an 8-core processor, so we can actually utilize all 8 cores and run parallel simulations on each individual cores itself. And also we have improved the simulation time nearly 15 times or in the past 5 years. And we have actually successfully ran millions of event models within a few minutes or something like that. And also we have added autosave option now, so that enables you to kind of make sure that whatever the model that you have constructed is saved somewhere, and you can actually provide the timestamp for saving those models as well, how often you want to save that model. And also we have provided polymorphism at the model level now, so which means whenever you connect a particular model or a particular block to a different block, the type of the data which is actually communicating between one port to another port is actually identified in the runtime, and the port type will be set automatically for that. Okay. And with regards to System C, now we support both hardware and system modeling methodology now. And also you can have a mix and match of System C plus VisualSim plus C models and all that in a single simulation model itself. Okay. And apart from that, we have now hardware in loop capability as well. We actually provide a Datagram API, so using which you can communicate between the hardware for conducting system level explorations as well. And now we have a concept of dynamic instantiation. For example, if you have a particular piece of block which must be instantiated 5 or 10 times, you don't have to redo the work again and again. You can actually model it in a particular dynamic instantiation block, and you can provide how many instance numbers as a parameter value. Then the simulator will actually automatically generate that many instances of that particular block itself. Okay. And with regards to the programming side, the scripting block now is actually is providing a lot of regex features or expression features, and also it provides ability to kind of adding and deleting an event while running the simulation model itself. And also you can perform instruction profiling using these scripting languages as well. The scripting language that we provide is almost 90% equal to C language, and in addition to that we have provided certain set of methods and functions to be able to quickly construct those queuing resources, computing power consumption, or creating an array or things like that. And the application interface block what we have right now supports both C, C++, and you can even run or you can even import DLLs and exe files into using these application interface blocks as well. And with regards to array itself, now the arrays are extremely popular and also very powerful, and this supports nearly 5 million or more than that of items that you can actually have in an array right now. And also we have added a lot of array related functions, either to access a particular data from a particular position, or to copy the data, or to perform computations on the array elements or things like that. So with regards to feature enhancements that we are working on right now, that includes documentation portion in which we are actually going to provide a cheat sheet which actually enables the designer to quickly look at these particular cheat sheets and quickly assemble up the simulation model. and they don't have to browse through the documentation and spend a lot of time with that. And also we'll be integrating VisualSim with modeling languages such as Modelica or SysML or UML, and we are in the process of doing that now. And with regards to software and firmware related things, we are actually providing a tool set for software schedulability for timing and space partitioning right now. And with regards to analysis part, we are actually providing an offline, we will be providing offline plotting with GNU plot there. And apart from that, we will be providing link view for the set of parameters and memories which are being used in the complete system platform itself. So with regards to the hardware side of it, so far we were focused more on architecture exploration and performance analysis and things like that. And now we are actually expanding these capabilities to thermal analysis as well. And we will be actually providing thermal analysis reports maybe in the next release or something like that. Okay, so this concludes this particular webinar, and now the session is open for question and answers, and I can see that most of the questions are being answered by our engineers, and if there are any, I'll take up from now onwards.